Welcome back to chapter number 4 of CCNA Cybersecurity Operations with me, Joachim Kärrestad from the University of Skövde. Once again, this is a very theoretical chapter with a lot of information in it, so I decided to split it up into 3 different lectures, where the first one is network protocols and addressing. We will then talk a little bit about connectivity and something called Address Resolution Protocol, or ARP, and we will end with some different services. So this might be a lecture that is a little bit long because we have about 27 slides to go through. But let's start simple with what a network actually is. So in terms of computer networks, a network is a collection of interconnected hosts, devices that are connected together so that they can communicate. So this includes servers, computers, printers, and intermediary devices such as routers and switches. You should know that networks come in all shapes and sizes. So we have everything from home networks or small office networks to larger organizational networks to the internet, which is undoubtedly the largest network in the world. And the internet actually means network of networks. So the internet is a lot of networks connected to each other. And on those networks, we have different types of hosts. And broadly classified, we have end hosts and intermediary devices, where end hosts is everything that's on the end of the network. And if you want to classify it further, you can say that it's clients that use services and servers that provide services. Intermediary devices can be described as devices that forward traffic. And this means, for instance, routers that forward traffic based on IP addressing or traffic between networks, and switches that forward packages based on MAC addressing or within networks. And we'll go through this deeper, of course. Modern networks there are many different requirements to them. There are many types of users that connect to the internet today. And you should know that different users have different network demands. You can consider that a gamer, student, financial officer, surgeon, and pilot will have very, very different demands on a network. This adds a high level of complexity. And what the internet does is that it provides end-to-end connectivity between any 2 devices that are connected to it. And much like in any other transportation system, there are usually multiple paths or routes and mediums between any 2 nodes. So if I want to go from Skövde, where I am, to let's say somewhere in the US, I can choose many different paths. I would most likely start by taking my car to the airport. From there, I would take a plane to perhaps Brussels or Frankfurt or London, and then I would take yet another plane to the US. In very much the same way, we have multiple ways for packet traversing the internet to take, and we have many different mediums that it can use, such as fiber optic cable, copper cable, or the air using wireless techniques. And a security analyst must be able to trace the origin of traffic entering the own network and must be aware of the different technologies that make up the internet in order to understand how communication on the internet occurs. So let's talk a little bit about protocols. So a wire or any other medium allows us to send signals between devices. We send ones and zeros. However, we need common rules for how to interpret the signals sent. So if we use a copper cable between 2 computers, we will actually send signals using electricity. But how do we know what is a 0 and what is a 1? So the receiving computer must, of course, know what's a 0 and what's a 1, and they must also know what 0s and 1s mean. And these rules of communication is governed by the use of different protocols that stipulate how communication should occur. So there are a number of different protocols that tells us different parts of how communication should happen over the internet. And we can group those together into something that we call protocol suites. And a protocol suite is a set of protocols that provide network communication services. So for instance, one of those protocols is the DHCP protocol that is used to automatically assign IP configuration to clients. And you can just see a small diagram here showing that there are a few steps of communication between the client and the server before this transaction can be complete. So when a client wants IP configuration, it sends out a discovery protocol. The server responds with an offer. The client sends back a request and eventually receives an acknowledgement. I realize that you don't really know what this is yet, but we will get to it. So when we are communicating, there are a few different message types that we can use. The first one is a unicast, and a unicast is a package that is sent from one host to one other host. When you know who you want to communicate with, and you communicate with that device only. Then we have broadcast, which is the opposite. It's then data sent from one host to all hosts in a network. Broadcast is basically the equivalent of going out to the town square and yelling out your messages for anyone that wants to listen. Finally, we have the multicast message type, which is data sent to a specified group of hosts. So let's talk a little bit about how we can organize and talk about protocols. There is something called the OSI model, or the Open Systems Interconnect model, which is a theoretical model of that describes how different protocols for different purposes can interact. And in this model, we have 7 different layers going from top to bottom. We have application, presentation, session, transport, network, data link, and physical. And if we begin with just a short description, the application layer is closest to the user and handles protocols that are close to us. One example is the HTTP protocol, which is used for web pages. Then we have presentation and sessions, a session that I will skip for now, and going down to the transport layer. So the transport layer is the first step in the communication layer, where we have where we handle addressing to different applications using port numbers, for instance, that we talked about in the previous lecture. And then we have layer 3, the network layer, where we have logical addressing, IP addressing. And then we have the data link layer, where we have physical addressing with MAC addresses. And then we have the physical layer, or layer 1, that handles media, signals and binary transmission, stuff like that. And we will look at this in even more detail in the upcoming lectures. So when we want to send package or when we want to send information from one computer to another, we actually have the data we want to send sent down through the entire OSI model, and different things happen in the different layers. So first we have the application layer, where we have the application data. So if we want to send a web page, for instance, we have the entire web page at the application layer. And then when we get down to through the different layers of the OSI model, additional data is added to this data to make sure that it can be sent over the network. This process is called data encapsulation. And once we get down to the physical layer, it has all of this information from the different OSI model layers, and it's being sent to the receiving end, where every part or every layer is being unpacked or de-encapsulated. So I'm not going to dwell in much detail about this now. We'll get back to this picture at the end of the network slides. And I also want to mention that there is another layer, another model that you can use as a reference model, that is called the TCP/IP model. And this image just shows you the 4 layers of the TCP/IP model and how they correspond to the layers of the OSI model. So if this is a point where you need to take a break, I fully understand you. I will go on to talk about addressing, which is the most important part of this lecture. So we actually have 3 layers of addressing, starting with the layer 2, the data link layer addresses. At the data link layer, we have physical addresses, or MAC addresses, and what they do is that they identify individual hosts on a local area network. So the data link layer addresses, or the MAC addresses, allows us to communicate on the local area network. But then when we want to communicate from our network to another network, we need a layer 3 address or a network layer address. And that's the IP address. And the IP addresses are addresses that can identify networks that devices are connected to. And then finally, we have the third layer of addresses, which is the transport layer or layer 4 addresses, and those are port numbers that identify services. So let's start with talking a little bit about Ethernet and layer 2 MAC addresses. So for the purpose of this course, Ethernet is a family of protocols that govern local area network communication. And that means that the Ethernet takes care of MAC addressing, encapsulating data into Ethernet frames. Ethernet frames is the name of data packages on layer 2. And it also handles media access control, which is translating or converting this frame into bits that can be sent over the network. And you can see the protocol or the frame here of an Ethernet type 2 frame. So an Ethernet frame will contain the destination MAC address. This is the MAC address that we want to send data to. And we have the source MAC address, the MAC address that this frame is sent from. Then we have a data package, which is basically the portion of the frame that has some actual data to it, and then the frame ends with a checksum, and the checksum is there for error checking. So using the checksum, we can calculate if this frame is undamaged and complete. So looking at the address format of the MAC address, the MAC address is a 48-bit binary value. But it's usually, or it's always expressed using 12 hexadecimal digits that can be represented in different ways. So usually you have groups of 2, like it shows here, that are separated by colons or by dashes. But you can also have this third format of a MAC address. All data that is traveling an Ethernet network is encapsulated in an Ethernet frame. And the source address is the local area network sender's MAC address, the MAC address of the source, and the destination is, of course, not what it says in this slide, but the MAC address of the intended target. So MAC addressing happens on layer 2, the data link layer. The layer 3 addresses, the network layer addresses, are called IP addresses. And at layer 3, data is encapsulated in IP packages, and IP addressing is added to the packages. And while we use the MAC addresses for addressing on the local area network, we need the IP addresses for addressing between local area networks. So let me just show you a quick example of how this happens. So this is a very simple network where we have PC0 here that wants to send a package to PC1. And to do that, he will first enter source and destination IP address. So it will use its own IP address as source IP, of course, 10.10.10.10. And as the destination IP address, he uses the IP address of the source, which is PC1, 192.168.1.10. But as source and destination MAC address, it uses, of course, its own source MAC address, which is all A's here. But as destination MAC address, it uses the next hop address, the MAC address that this package should be addressed to on the local network. So for this package to reach PC1, it will have to go to router 2. So router 2 is the destination on the local network, right? And therefore the destination MAC address in this case is the MAC address of router 0. So all A's but ending with BB. A very, very short and brief example that we will talk more about later. So let's talk about some of the characteristics of IP or IP version 4. So it's connectionless and unreliable, meaning that it's a best effort protocol. And what this means is that IP in itself doesn't really care if a package comes to the receiving end or not. It just sends out the package to where it should go and hopes for the best. Pretty much like when we send a letter with a post office. There is no way for us to know when it reaches the source or the destination. IP is also media independent, meaning that IP doesn't care about whether the package is sent over fiber or copper or over something else. And the structure of the IP address is a series of 32 bits, usually grouped in 4 groups of 8 bits. And you usually represent it in a decimal form that we call dotted decimal, such as 192.168.110. Talking more about the IP address, the IP address is divided into 2 parts actually. So first we have a network portion that identifies a network, and the network portion of the IP address is the same for all hosts on the local area network. Then we have the host portion that identifies a single host on that local area network. So the network and the host part is decided by something that is called a subnet mask. And this net mask allows or follows the same structure as the IP address. The thing is that if we look at this picture, you can see that you have the subnet mask down here, and the ones in the subnet mask shows which bits of the IP address that belong to the network portion of the IP address. So in this case, we have all ones all this way, meaning that all of those bits in the IP address belong to the network portion of the IP address. Traditionally, we've used something that is called CLASSFUL IPv4 addressing, which is basically just a way of telling how big a portion of the IP address that belongs to the network address and to the host address. You can read about this on your own if you like to dwell deeper into that. I also want to mention public and private IP addresses. So private IP addresses are IP addresses that cannot be routed on the internet, and those are intended for internal use. And the IPv4 addresses that are considered private are those listed here. I'm not going to babble them up for you. And all other addresses, or most other at least, are public addresses, and those are addresses that can be routed on the internet. So the idea is that we have we have private IP addresses within our network, and then we have a couple of public addresses that the whole network uses together that you can borrow when you need to communicate with the internet. So let's mention something that is called forwarding decision. So with all this addressing, I'm sure you realize that whenever a computer needs to send data to another computer, it has to figure out where to send it. More importantly, we have those intermediary devices, the routers, that may be connected to many networks, and they need to know which link to send a package to. So when a host needs to send data, it makes what is called a forwarding decision, a decision about where to forward the data. And you can choose to forward data to yourself, to the local network, or to a remote network. And when you need to forward a package to a remote network, it's sent out to the default gateway, which is, in terminology, the closest router. And the router then decides on the next hop based on something that is called a routing table. And a routing table is basically a list of information about networks and where the networks are located. So that's it for IPv4 addresses. Unfortunately, we happen to be out of them since a few years back, so now we have something that is called IPv6. And the difference between IPv4 and IPv6 is mainly that we have much more addresses, a much larger address space with IPv6. So while IPv4 is about 4.3 billion addresses, IPv6 contains close to an infinity of addresses. IPv6 addresses are 128-bit long, and they are commonly represented using 8 groups of hexadecimal digits. So the way that they look are something like you can see in the full address box here. But the thing is, with IPv6 addresses, you can compress the addresses so that they are easier to write and read. And what you can do is that you can omit leading zeros in every group. So you can see that the address is grouped here. There are 4 hexadecimal digits in every group, and they're separated by colons. So in every group, you can remove all leading zeros. So for instance, instead of having 0001, you can just type a 1 as down here. Then you can omit 1 segments of all zeros. So you can see here, from this 1 all the way to the end, it's only zeros, and you can remove all of those by substituting them for a colon. So instead of having this very long address up here, we can just shorten the address so it says acad:1:1, and that's also a full IP address. There is a network and host portion to an IPv6 address as well, and the size of each portion is variable, and it's identified by adding -x to the IPv6 address. So for instance, having this acad:1:1 address and adding -64 will tell us that the first 64 bits are for the network address, and then the remaining bits are for the host address. And the typical separation is actually -64, meaning that half the address is for the network and half the address is for the host. So that was a messy lecture, but I hope you managed to catch most of it. Feel free to leave comments as always, and see you next time for part 2 of this network lecture.